originated the idea of dividing a circle into 360 degrees and then subdividing each degree into 60 parts called minutes, and each minute into 60 parts called seconds. The first astronomers to make long-term written records 6,000 years ago. The Babylonians were able to use the long record of observations to see regularities and patterns in the motion of the moon and planets. They found each planet's zodiac period, which is the time needed for the planet to go from a particular configuration. The Babylonians also discovered and measured the longer intervals of time required for a planet to return to the same position with respect to both the sun and the stars. The Egyptians developed and used astronomy entirely for practical purposes, such as developing a calendar to be used to predict the Nile flood. Many Egyptian temples and monuments, such as the Great Pyramid, were aligned with respect to the cardinal points, north, south, east, and west. The temple Amun-Ra Karnak were aligned with respect to the rising and setting of the sun at the time of the summer solstice. The first of the Malaysian astronomers was Thales, who traveled to Egypt to gain ancient knowledge. The most famous story about Thales was that he predicted a total solar eclipse. The eclipse took place during the battle between the Lydians and the Persians in 585 BC. He developed a model for the solar system, including two features that marked a permanent break from previous thinking about the universe. The Pythagoreans rejected the idea that the Earth is flat and adopted the notion of a spherical Earth. That all celestials must be circular because circular motion is the only kind of motion that can be repeated forever and is suitable for unchanging bodies such as the moon, sun, and stars. One proof proposes that falling objects move towards the center of the Earth. In his third argument regarding the Earth's shape, Aristotle pointed out that the Earth's shape must be a sphere because some of stars can be seen in Egypt but not in Greece. Showed that it is possible to use geometry to find the distance to the moon and the relative distances and sizes of the sun and moon. He also calculated that the sun has a diameter about 7 times as large as the Earth. It may have been the immense size of the sun that led him to propose that the sun is stationary and that the Earth orbits the sun in a circular path. He used geometry to calculate the size of the Earth. The main limitation on his ability to find the circumference of the Earth was his dependence on other people's measurements of the distance between two cities. Hipparchus discovered a new star. This discovery prompted him to begin the task of making what was probably the earliest systematic catalog of the brighter stars. Although his catalog had been lost, descriptions of it suggested he gave positions and an indication of brighter stars for about 850 stars. His major accomplishment was the completion of a system that could accurately account for the motion of the planets using a combination of regular circular motions. As a geographer, he invented terrestrial latitude and longitude. He was the first to orient maps with north at the top and east at the right. Ptolemy's method of describing the brightest of stars, called the magnitude system, is still in use. Ptolemy's most influential contribution to astronomy, however, was the geocentric model of the solar system. Made and recorded observations of eclipses at least as long as the 13th century BC. The Chinese also recorded other conspicuous astronomical events such as meteor showers. The extensive observational records enabled Chinese astronomers to determine accurately the length of the year, to discover precession, and to use eclipse cycles to predict when eclipses would occur. Many Mayan monuments and buildings were aligned to the position of sunrise and sunset at the equinox and solstice. The Mayans aligned buildings and built lines of sight pointing towards the northmost and southernmost risings of Venus. They also prepared extensive tables of risings of Venus and of lunar and solar eclipses when they were able to predict in advance. He proposed the first fully developed heliocentric model of the solar system. In one of his books on economics, he developed an early theory of capitalism and was the first to show that bad money drives out good, which later became known as Grimsham's law. Copernicus wrote an outline of a sun-centered theory of their solar system, and he distributed it to a friend. His theory probably would have never been published had his outline had not been read years later by a German astronomer. It's ironic that Tycho actively opposed the heliocentric model. Given his great reputation among his contemporaries, his opposition delayed the general acceptance of Copernicus. He was the first scientist to understand the value of multiple observations of the same event. Tycho's accurate observations led him to reject the heliocentric model of the solar system. Tycho looked very carefully for stellar parallax, the annual apparent change in the position of a star caused by the motion of the Earth around the Sun. Kepler's main discoveries about the nature of the planetary orbits were made while trying to account for Tycho's observations of Mars. Kepler discovered a mathematical relationship between the distances of the planets and their period of revolution. His discoveries are summarized in Kepler's law of planetary motion. Galileo is often credited with the invention of the telescope and being the first to turn it to the heavens, but neither was true. The telescope was invented in 1600s, but in the summer of 1609, when he first started his experiments, it had long been accepted that heavy objects fell faster than the lighter ones. His works on gravitation, for instance, remained unpublished for about 20 years. Newton's discoveries about gravity, motion, and orbits of the planets were finally published. Newton discovered the laws of inertia, the laws of force, and the laws of action and reaction. The mathematical description of centripetal acceleration is produced by the force of gravity exerted by the sun in 1666. In 1705, in his work, he showed that comet sightings of 1456, 1531, 1607, and 1682 were so similar that they must have been the same comet returning. He predicted that it would return in 1758. He died on January 14, 1742. He did not survive to see the return of which later was named Halley's Comet on Christmas Day in 1758. One of his most famous equations ever written came from Albert Einstein, E equals mc squared. Energy is mass times the squared speed of light. This equation shows that mass can be turned into energy. Because the speed of light squares is such a high number, even a small amount of mass can be turned into a lot of energy. This means, for example, that there is enough energy in a glass of water to give power to a city like London for a whole week. The problem is how to get the energy out of the mass. This equation led to the building of the atomic bomb. The first bomb only had 0.6 grams of mass, but scientists turned it into enough energy to destroy a whole city. There are a few problems with the model. However, for example, according to classical physics, the electron orbiting the nucleus should lose energy until they spiral down into the center, collapsing the atom. Bohr proposed adding to the model the new idea of quanta put forth by Max Planck in 1901. That way, the electrons existed at set levels of energy, that is, at fixed distances from the nucleus. If the atom absorbed energy, the electron jumped to a level further from the nucleus. If it radiated energy, it fell to a level closer to the nucleus. His model was a huge leap forward in making theory fit the experimental evidence that other physicists had found over the years. Austrian-born physicist and recipient of the 1945 Nobel Prize for Physics for his discovery in 1925 of the Pauli exclusion principle, which states that in an atom, no two electrons can occupy the same quantum state simultaneously. Pauli made major contributions to quantum mechanics, quantum field theory, and solid-state physics, and he successfully hypothesized the existence of the neutrino. In addition to his original work, he wrote masterful syntheses of several areas of physical theory that are considered classics of scientific literature. German physicist and philosopher who discovered a way to formulate quantum mechanics in terms of matrices. For that discovery, he was awarded the Nobel Prize for Physics in 1932. In 1927, he published his uncertainty principle, upon which he built his philosophy and for which he is best known. American astronomer who played a crucial role in establishing the field of extragalactic astronomy and is generally regarded as one of the most important observational cosmologists of the 20th century. Hubble is known for showing that the recessional velocity of a galaxy increases with its distance from the Earth, implying the universe is expanding, known as Hubble's law.